Module 6 covers secure software and system architecture for ICS. Upon completion of this lesson, students will be able to describe the strategies for secure software development, understand the various design principles and secure coding activities, describe the 6 basic ICS security concepts that need to be covered by testing processes, describe the need for an ICS security architecture and the various segmented zones of a Purdue control framework, describe the function of each level in the cell area zone and the enterprise zone, and understand the ICS security controls. First, we will investigate ICS secure software development. Industrial control systems, ICS, such as those that operate our nation's critical infrastructures, are beset by challenges that affect the security of their real-time or near real-time operations. As documented in the 2016 ICS CERT Year in Review, the Industrial Control Systems Cyber Emergency Response Team, ICS CERT, responded to 290 incidents reported by asset owners and industry partners in 2016. One of these incidents is a malware attack on a water control system facility that enabled a persistent, malicious remote access. Also, in fiscal year 2016, the first known cyber attack on a power grid that resulted in physical damage was discovered. Evidently, a mechanism to proactively prevent these cyber attacks from materializing is needed. It is imperative that security must be instilled into the mindset of developers and not make security an afterthought. It is incumbent that software engineering education must include secure design, secure coding, and security testing to supplement the traditional concepts on software. Secure by design. This strategy advocates the application of the following methodologies at onset. Designate a security personnel who is responsible for all security issues. Require security training for all personnel. Make sure that the threat models are in place after the completion of the design process. Stay within the design and coding guidelines. Correct bugs that deviate from the guidelines. Continuously improve the guidelines. Perform regression testing. Simplify the code and the security model. And perform penetration testing. Secure by default. This strategy can be achieved by the following: not installing features and capabilities by default, allowing least privilege to users, and applying adequate protection to resources through appropriate access control mechanisms. Secure in deployment. This strategy advocates adhering to the following guidelines. Ensure that the application enables the administration of security features. Create quality patches for discovered vulnerabilities as soon as possible. And provide the user sufficient information through a help facility or error message on securely using the system. Learn from mistakes. Mistakes can be beneficial if taken as learning opportunities. In security, these mistakes can be security incidents or system vulnerabilities that are discovered. It is important to understand how and why these mistakes occur. It is equally important to learn from these mistakes to prevent them from reoccurring. Minimize the attack surface. The attack surface refers to the number of ways an attacker can penetrate the system. By minimizing these opportunities, the probability of a successful attack gets slimmer. Minimizing the attack surface entails enabling a secure default installation of the system. If a feature is not necessary for the normal operation of the system, it should be disabled. Use defense in depth. Defense in depth is a series of defense mechanisms that are used to protect a system from malicious intrusions. The idea is to build a series of defense mechanisms in a manner that if one fails, another will be in place to prevent the intruder from advancing. Use least privilege. The least privilege principle refers to the concept of granting the minimal user privileges on a system based on what is needed by the user to effectively perform his or her functions. For example, a user who performs data backup does not need administrative privileges such as installing applications and creating user accounts. Assume external systems are insecure. This principle relates to the fact that any input originating from an external source could potentially be an attack vector. A client could potentially harm a server with harmful code masquerading as a legitimate request. Likewise, a trusted server, if compromised, can potentially be a carrier of malicious data. Plan on failure. There is no such thing as a perfect system. The constantly evolving hardware and software can cause one or both to fail. It is paramount that security contingency plans must be in place to alleviate the impact of such failure. Fail to a secure mode. Failure can place the system in a secure or insecure mode. Failing into an insecure mode could enable the loss of data integrity and/or confidentiality. It could also place the system in a highly vulnerable state that can lead to a successful attack. Failing securely protects the system and the information within from any disclosure or tampering. Further, these failures must be properly logged for future reference. Never depend on security by obscurity. Security by obscurity relies on the secrecy of design and implementation as the main method of providing system security. An interesting, although a bit appalling example of this is to secure an online poll by not allowing anyone to vote more than once. In this case, the security mechanism seems to be hidden in cookies. However, this can easily be circumvented by deleting the cookies. Do not mix code and data. Many of the security vulnerabilities are enabled due to the notion of mixing code with data. Examples of this include the mingling of macro codes with data in Microsoft Office applications, the commingling of scripts with email, and the web page text with JavaScript. Fix security code correctly. When a security flaw is discovered, assume that it appears in other places as well. Always assume that the design or code pattern of insecurity persists and will have to be eradicated everywhere it exists in the application. It is better to fix the security code as early in the design or implementation as possible. After completing the secure design processes, implementation steps that include secure coding activities come next. These activities, as described by Grebe, are as follows. Request validation. This activity includes user authentication and authorization, request cleansing, and data encapsulation. It is imperative that proper user authentication for system access and authorization for data retrieval is enforced. In ICS, this security mechanism must be applied not only to the system devices, but also to the HMI and the historian as well. Requests, especially those made on the historian, could possibly carry malicious strings that facilitate SQL injections. Thus, requests must be scrubbed of unexpected strings or special characters. Encapsulation is a technique of shielding data from direct access and making them accessible only through class, mutator, or accessor methods. Limiting data access through these methods provides a mechanism for defense in depth. Exception handling. In many modern programming languages, error handling mechanisms are provided. It would be best to judiciously handle those so-called exceptions to let the application perform a graceful degradation without revealing messages that can be used by the adversary to craft an attack. Creation of self-monitoring code. Self-monitoring code is another defense in-depth mechanism that automates the process of monitoring security events. In addition, the application implementation must include robust alert and recovery features to effectively handle security incidents. Recognition of the faults of programming languages. Certain security faults are prevalent to most programming languages. These limitations are extensively documented in published literature. Developers, at the very least, must be familiar with the following faults. Buffer overflow. A buffer overflow is an application or system runtime condition in which an attempt is made to write more data to a buffer than it can hold. This attempt to write data outside the bounds of a block of allocated memory can cause a program to crash or the execution of malicious code. Unsafe functions. Unsafe C or C++ function calls are the most notorious and potentially dangerous functions. These functions have safe counterparts that can be used instead. Software testing is the process of verifying and validating that an application or system software fulfills all the specifications and performs all the functions for which it is intended. While the process of verification is mostly static in nature, the process of validation is dynamic. Verification methods include code inspections, design walkthroughs, and document reviews. Validation methods include black box testing, gray box testing, and white box testing. In this lesson, we will focus on ICS software security testing. ICS software security testing is basically a type of software testing that centers on checking whether the applications that control the operations of ICS are secure or not. It is making sure that ICS software behaves in face of a malicious attack. There are 6 basic ICS security concepts that need to be covered by testing processes. Confidentiality. This concept deals with the need to keep information secret. In ICS, it is not as important as integrity and availability. Integrity. This concept requires that information be free from corruption. It is very critical that data going to and coming from controlled devices and peripherals are tamper-free for secure and safe operations. Availability. This concept requires the availability of devices and information at all times to enable effective and efficient operations. Authentication. The authentication of users and devices must be enforced at all times. Older ICS systems have been designed with very few security features, such as that of authentication. Another challenge to security practitioners working on ICS is to redesign and implement application software with authentication mechanisms. Authorization. This concept specifies the access limitations of authenticated users and devices. It implements the security principle of least privilege. Non-repudiation. This concept ensures that operational control or actions can trivially be associated with a unique device or user. ICS software security testing may involve additional types of traditional software, such as black box testing, unit testing, integration testing, functional testing, regression testing, scalability testing, stress testing, and so on. In what follows, we will look closely into the usability testing of a human-machine interface, HMI, and integrity testing of a data historian, both of which are principal components of an ICS. HMI usability testing. HMI usability testing, a black box testing technique, checks the level of acceptability of the HMI by the users. The parameters involved in this type of ICS software testing are the following: the navigation setup, the layout of controls, the speed, the content, and the ease of use. Data historian integrity testing. Data historian integrity testing refers to the verification process that data being stored by the ICS is not compromised during saving, updating, restoring, or retrieving. This type of testing is intended to uncover design flaws that may result in data corruption, unauthorized data access, lack of data integrity across multiple tables or databases, and degradation in performance. We now explore ICS security architecture. As previously described in Module 1, it is best to separate the operational technology OT network from the information technology IT network. Network traffic activities, such as web browsing, emails, FTP, and cloud services, must be allowed only in IT networks and never in OT networks. Furthermore, inside the OT network, further segmentation of the network into layers could provide extra defense in-depth mechanisms. This segmentation should be based on factors such as management authority, uniform policy and level of trust, functional criticality, and the amount of communications traffic that crosses the domain boundary. In order to fully appreciate the reference logic architecture for a secure ICS network, we must first look into the Purdue Enterprise Reference Architecture model as shown in the figure below. This model of a control hierarchy logical framework is developed by the International Society of Automation, ISA 95 Committee for Manufacturing and Control Systems Security. The control hierarchy logical framework is divided into 4 zones: the cell area zone, the manufacturing zone, the demilitarized zone, DMZ, and the enterprise zone. The availability and performance requirements are most distinct in the cell area zone. This zone is further subdivided into the following 3 levels. Level 0. In this network level are the sensors, actuators, drives, and any other ICS devices that require real-time I/O communications. Level 1. The basic controllers are found in this level of the cell area zone. These devices provide control functionalities such as batch, discrete and analog, drive, process, basic human-machine interfacing, and safety. Level 2. This level includes the control room, controller status indicators, ICS network application administration systems, and other control-related applications such as the supervisory controller and the historian. With regard to security, the cell area zone is particularly susceptible to the following attacks: unauthorized access, MAC flooding and spoofing, spanning tree attack, VLAN attack, DHCP starvation, and DHCP impersonation. The purpose of the security design is to provide the following functions to prevent the realization of these attacks: secure network access by devices. By limiting access only to authenticated and authorized devices, the risk of process interruption can be mitigated. Protecting key cell area network infrastructure and functions. By enabling the built-in security features of network devices, attacks such as the spanning tree attack, VLAN attack, DHCP attack, and MAC attacks can be prevented. The manufacturing zone includes the management functions for workflows and other IT services such as DHCP, DNS, file management and storage, and distributed directory information. The workflow management functions may include production scheduling, reliability assurance, site-wide control optimization, security management, and network management. The DMZ is not included in the original Purdue model, but was put in place by Cisco and Rockwell Automation in their converged plant-wide Ethernet architecture. This zone provides the separation of the enterprise, layers 4 and 5, from the ICS network, layers 0, 1, 2, and 3. This separation is essential to ensure that network traffic in the enterprise does not affect the real-time availability and security requirements of the ICS network. Firewalls are deployed to enforce the separation and to act as defense in-depth mechanisms. Additional functions that are provided by this zone are Unified Threat Management, UTM, Authentication and Authorization, Application and Data Sharing via Access Replication, or Terminal Services. Many enterprise applications have been implemented to enable more efficient manufacturing, as well as Internet applications to facilitate business-to-business, B2B, or business-to-consumer, B2C, communications. These applications may include Internet-based Enterprise Resource Planning, ERP, Consumer Relationship Management, CRM, and Supply Chain Management, SCM, systems. Although these newfound conveniences provide some enhancement to productivity, they also have increased the cyber security risk, not only for the enterprise network, but also for the ICS network as well. This zone is further subdivided into two levels, levels 4 and 5. Level 4. This network level includes the manufacturing facility IT services, which may include scheduling systems, material flow applications, manufacturing execution systems, MES, and local IT services, phone, email, printing, security, and monitoring. Level 5. In this network level, management applications such as ERP, SCM, CRM, and so on, productivity software such as document processing, spreadsheets, presentations, and so on, and connectivity services such as internet access, virtual private networks, and so on are found. The Purdue model is further defined in the ANSI ISA 62443-2-1, 99.02.01, 2009, Security for Industrial Automation and Control Systems, establishing an Industrial Automation and Control Systems Security Program standard. This standard has been developed in large part from a previous technical report produced by the ISA 99 committee, ANSI ISA TR 99.00.02 2004, integrating electronic security into the manufacturing and control systems environment. This standard is a complete security lifecycle program with best practices for developing and deploying policy and technology solutions to address security issues in control systems. In this standard, segmentation of control system layers is realized through the utilization of zones and conduits. A zone is a grouping of logical or physical assets that share common security requirements based on factors such as criticality and consequence. An asset in a zone is designated with a security level capability, which should be at least equal to the requirement level for that zone. If it fails to meet this minimum requirement, additional security measures must be implemented on that asset. Communication between zones must be done via conduits. A communication conduit facilitates the controlled access to zones, prevents the propagation of malware, resists denial of service attacks, and protects the integrity and confidentiality of network traffic. The built-in controls in a conduit are intended to mitigate the difference between a zone's security level capability and its security requirements. By focusing on conduit mitigations, the tedious and costly process of upgrading every asset in a zone to meet the security requirements is circumvented. Another adaptation of the Purdue model is shown in the figure below. This recommended secure ICS network architecture utilizes the same zones and conduits that were suggested by the ANSI ISA 62443-2-1 standard. The placement of the network firewalls at strategic places facilitates the implementation of communication conduits. The ICS architecture security zones are depicted in the figure. Note the two main zones, the enterprise security zone and the manufacturing security zone. The segmentation of business, IT, and OT networked information systems is based on the following basic functions. The enterprise security zone. This zone provides the connectivity to the internet, peer locations, and backup or remote off-site facilities. Communication networks and servers such as email servers, domain name system DNS servers, web servers, database servers, and other IT business systems. The internet-facing DMZ is the untrusted section of this zone. Manufacturing security zone. This zone consists of the majority of monitoring and control functions. The operational support, such as data historians and HMIs, and manufacturing management systems are found in this zone. The manufacturing zone provides the required connectivity to the enterprise zone and operational control to the field devices. The priority of this area is high. Risks are associated with its direct connectivity to any external systems or networks. Cell security zone. The cell security zone contains systems used for local or remote area control, such as HMIs and PLCs. Basic input and output devices, such as actuators and sensors. In most modern control system networks, these devices will likely be accessible through an ICS protocol that is encapsulated within the Transmission Control Protocol Internet Protocol, TCP/IP. It may also include safety instrumented systems, SIS, on a separate network to minimize the risk of being compromised. The following are basic ICS security controls that need to be implemented. It is imperative for an organization to implement effective security controls that could mitigate its risk exposure. Controls that assert the following security best practices are important. Create an inventory of all devices. Create an inventory of all applications and system software. enable secure configurations for hardware and software on mobile devices, laptops, workstations, and servers. Implement a continuous vulnerability assessment and remediation program. Perform a system audit and minimize the use of administrative privileges. Identify, minimize, and secure all network connections to the ICS. Additional ICS security controls are the following. Harden the ICS and supporting systems by disabling unnecessary services, ports, and protocols. Enable available security features. Implement robust configuration measurement practices. Perform continuous monitoring and assessment of the security of the ICS, networks, and interconnections. Implement a risk-based, defense in-depth approach to securing ICS systems and networks. Manage the human aspect of security by establishing expectations for performance, holding individuals accountable for their performance, establishing the necessary usage policies, and providing ICS security training for all personnel involved.